Thank you, Judith. It's good to just share something about this thing that's called AfricaArray. It's been running for over a decade here, and Wits is the leading institution. And every year we have our AfricaArray workshop where we have people from all over the world coming along, usually about 80 people, but it's perhaps not as well known in the school as it might be. So I'll be talking about work that we've been doing over the last few years with various of our PhD students. So our goal here really, it started in about 2005, was to create this public-private partnership over here to promote geoscience in Africa. So that, and not just geophysics, but also other forms of atmospheric science, space science as well. But initially the idea was to start with geophysics. And you'll see AfricaArray is not just you'll see it's an array of observatories, it's an array of projects, it's an array of institutions. So the people who started it were Penn State, Wits University, and then our Council for Geoscience in Pretoria. And since then we've involved a lot of other organizations in Africa. So let's look and see what we've got here. Our backbone network over here is an observatory network, 51 geophysical observatories in about 19 countries, now it's 21 countries, because we've added a station in Morocco and another one in Cape Verde. But most of them, 48 of them, have got seismic stations, but about half of them have also got weather stations there and continuous GPS stations. And from these weather stations, that allows us to do science in the area of atmospheric studies and climate change. And we've just been recording for maybe 2 or 3 years right now, so that data series is starting to build up. And then we also, from our GPS stations, it also allows us to get information such as the soil moisture, atmospheric moisture, and also look at space weather, the effect of the cosmic rays on the ionosphere. And so we started to get activities going in that area as well. So really you can see they spread over there in Ghana, in Cameroon, in Nigeria, in Ethiopia, all the way down the East African Rift, in Madagascar as well. So this is what we call our backbone network. And then in addition to this, and we'll talk more about it later, is we have temporary arrays where we borrow instruments from a group usually in the US called Incorporated Research Institutions for Seismology, and we get bunches of equipment and we put them out for maybe 2 or 3 years. And so we have temporary arrays as well. But this is a typical field array over here. These are stations that were in Mozambique over here, and we have Ilio from Mozambique who's been to some of these sites over here. But down here you can see there's a vault that's been dug down here. We try to get it as close to bedrock where we can. And that green thing over there is a seismometer. That's a seismograph. And so you have it, so it can pick up the vibrations. That's just some insulation that you put over it to protect it from changes in temperature. And then on this, perhaps either you bury it in a box in the ground, or in this case they've got a little hut over here where you have data loggers. This is a data logger, batteries, we have solar panels on the roof, and there's a GPS antenna there as well. So if this setup like this costs a couple of 100,000 rand, all the equipment to have it built, and it's set out there and it records data continuously. So every 40 times per second, it is taking a measurement of a north-south component of motion, east-west component, and a vertical component. And that's stored on a memory card, and every month somebody will go and download the data. A few of our stations, in South Africa, they're connected to the GPS network, so we can download the data in near real time, a couple of times a day if we need to. So why do we do this? Well, in terms of the research, some of the research work is directed towards mineral resources, and I'll describe a little bit of that. Other of the work's directed towards geohazards, trying to understand earthquake risk better, particularly along the East African Rift. Also volcanoes. We do volcano monitoring in the Virunga volcanoes in the DRC, and quite a lot of it, and that's what I'll be mostly talking about today, is curiosity. How does the African continent work? So the kind of issues that we look at over here are trying to understand, all these words, plumes, super plumes, hotspots, large igneous provinces, intertectonic basins, East African rift system, bushveld complex, kimberlites. But how did this all work? What is the structure of the continent and its roots, and how did it get there? How did it evolve? And these are just some of the big issues which here at Wits we know much about, but we know that Southern Africa and East Africa is abnormally high, and the question is, why is it so? What has caused the continent to bob up like this over the last few tens of millions of years? So that's one of the big questions that we are trying to work on in AfricaArray. So here's just a view, and today in this talk I'm just going to be touching on some of the work that we've been doing all over Africa, such as work here in the Waterfront Basin, the Bushveld Complex, the Congo Petra, the East African Rift, the Khartoum Basin, and also the Cameroon volcanic line. So that's some of the issues that I'll be touching on. But here as seismologists we have a whole lot of toolboxes, but really what I'm talking about here is mostly using earthquakes as our energy source. So this is what we do. We do passive monitoring and we see what nature throws at us. And every day there are perhaps 3 or 4 earthquakes somewhere in the world that are bigger than magnitude 5, and we use earthquakes like that, and their waves that spread out through the world, through the earth, and they come up and they will illuminate Africa from below somewhere here, and they allow us to get images of our continent. And there are a whole host of different geophysical tools that we use, different methods, and I'll describe them very briefly as we go through this. And I'll show you examples of reflection seismics and what we call receiver functions and tomography as well. And this is not the first time this has been done in South Africa. From 1997 to 1999, there was an array of seismographs we put out from Cape Town all the way into Zimbabwe. And at that stage, this was the biggest experiment of its kind like this anywhere in the world. And this was done together with MIT, Massachusetts Institute of Technology, and the Carnegie Institute of Washington, and was supported by mining companies like De Beers and Goldfields. And that delivered some very, very interesting results as well. Now, since then, there's a bigger program called USArray like this, which has now been covering the whole of the continental, the USA. And that's now a lot bigger array than we ever had here. Of course, what we've been trying to do, and you'll see later on, is now fill out this array. And right now we've got an array of 25 stations in Botswana, which is filling in that gap, and then 10 stations in northern Namibia. So we're patching onto this array, and gradually we've just finished deployments in Mozambique. So gradually, as time goes by, we're filling in the picture as well. Right, and this is the kind of picture that emerged from the studies in the late 1990s over here, but to get a good picture of the crust mantle boundary, the MOHO, and then also look at the roots of the continent to see how deep the lithosphere extends underneath southern Africa. And so there were some very interesting results over there. And what we're doing in AfricaArray is pretty much taking the same approach, but not just confining it to southern Africa, but over the entire continent, and of course using new techniques and more sensitive instruments than were available 20 years ago. So, of course, we don't work just with our seismic data, but we have other kinds of geophysical data like aeromagnetics that we can use, and gravity data. And then also what's happened over the last 20 years, there have been programs to collect what we call magnetotelluric data. And this has been done mostly by the Dublin Institute for Advanced Studies, and also with a German group at the Geoforschungszentrum over here doing various profiles collecting magnetotelluric data, and also giving us deep views into the Earth down to depths of several hundred kilometers. And so certainly what we get from our seismics, we try where possible to integrate this with our magnetotellurics. Magnetotellurics has only really been done in southern Africa here, and not yet to any great extent in the rest of Africa. Every year, as I said, we have our AfricaArray workshop, where we typically have about 40 seismologists from elsewhere in Africa, from our AfricaArray partner countries, coming to join us. So from Egypt, Cameroon, Nigeria, Ghana, wherever, Ethiopia, all over. And this is where we really share our ideas, what we've learned, plan our projects, and get together. Next year we'll be having ours probably in the week beginning the 18th of January. So this is the community that we've developed over the last 10 years or so. Right, our sponsors over here, of course, are the supporting programs, of course, our universities, Wits, Penn State, and also the Council of Geoscience. And we get a fair amount of money, particularly from the American National Science Foundation, from our NRF grant, and also we get from the US Department of State, and even things like the United Nations Office for Outer Space Affairs. They're very interested in our GPS network over here. So these are some of our major sponsors, but we have many other sponsors for various projects. What we've achieved over here, we have a whole bunch of MSc students, both here at Wits, at Penn State University, and other universities have come through as well. We have our stations up in place. We have our as I said, 51 permanent stations in 19 countries, and we've had over 100 of these temporary stations out for 2 or 3 years, and we have partnerships with universities in Africa, in US, Australia, Japan as well, over here, and of course produce papers where we can. A few comments over here. What we've done in the Wits over here, well, that's just to introduce some of the students that we've had. 2 years ago, Busaeldridge graduated, and we were very proud. They were the first 2 black South Africans to get PhDs in geophysics, so that was a good day for them. And Musa's work, I'm sure you've seen it, I won't talk much about it, but he's been using reflection seismics, which is a very high resolution technique, to image the Wits basin. So he's spoken about that here before, so I'll skip over that. But let's talk about what Musa's been doing. Musa's an employee at the Geological Survey for Council for Geoscience. Sorry, Eldridge, thank you. And one of the questions that he was looking at, this is the work that Sue, of course, has been very driving, is the question, is the bushveld continuous in the middle, or is it just 2 dipping limbs of the bushveld? And in that case, is the mantle level, or is it depressed? Because both these models can more or less match the gravity, but perhaps seismics will give us a better idea. So what Eldridge did is he used a technique where we use what we call receiver functions. Now the whole idea is if you've got a distant earthquake, an earthquake perhaps between 3,000 and 10,000 kilometers away, when the energy comes in, when the body wave, when the P wave comes in, it comes in at quite a steep angle, and when it gets to a boundary like that, you'll find the energy gets transmitted, and it gets refracted, so you can see the rays are being bent, but also the energy gets converted. If it's a P wave energy, part of it will be converted to an S wave. And so you'll get your incoming direct P wave, and a few seconds behind it, maybe 5 seconds behind it, you'll get the part of the energy, the P wave that was converted to S wave energy, will come in trailing behind it. And then, of course, when it gets to the Earth's surface, it's got nowhere to go but back down again. So it bounces down again and comes back up again, so you get a whole series of reverberations. And we're able to see these things, extract these things from our seismograms over here, and from that we can work out things like what is the thickness of the crust and what is the nature of the crust. And so this is what Eldridge used. Now, in the time of the Massassi experiment in the late 1990s, it was just a very simple way of doing it. You see your first arrival here, that's the direct wave, and then maybe 5 seconds later, which indicates a depth of perhaps 30 to 40 kilometers, you see the S wave coming in, the conversion at the MOHO. And what has happened in the since then, of course, is new techniques that have developed to allow this to be interpreted in a great deal more detail, and that's what Eldridge did. And so over here you get this function over here. This is what we call a receiver function. So it's a seismogram that's had a bit of magic done to it over here to bring out the signal in more detail. And also what we do over here is we don't just take, if you've got one station in one place, let's say at Wits, you'll get earthquakes coming from different directions. You'll get them coming in from Chile, and you'll get them coming in from Indonesia. And where they arrive, where they pierce the MOHO, are in quite different places. In the one case it will be 30 kilometers to the northeast, and the other one somewhere to the southwest. And so it's possible to sort those out and to then see if there's any difference in structure either to the northeast or the southwest, and so do a more comprehensive interpretation. And then not only are you recording the body waves that come down below, but there's a whole set of waves called surface waves that travel around the surface of the Earth, and they've got this peculiar property that different wavelengths travel at different velocities, and we call that dispersion. And if we analyze the dispersion over here, it can tell us also something about the deep structure of the Earth. So what we do over here in this new technique we call a joint inversion, we take both those data sets and we find the model that gives us the best match to both of them. And what you can immediately see over here, it's possible for us then to not only look at data from different directions, so it gives us some three-dimensional structure around our site, but combining the two data sets, it allows us to pick up a lot more detail of the structure of the Earth's crust and upper mantle, compared to just picking the MOHO depth. So you can see more detailed structure there. And so this is what Eldridge did with the data over here. He analysed it together. He took the stations that had been deployed over the Bushveld complex over here during the South African seismic experiment. All the data has been stored and archived, so it is really taking existing data, old data, and reprocessing it using smarter techniques. And over here, Those are the stations, about 100 kilometers apart on a grid, 100 kilometers apart, putting them together and then extracting certain profiles to look and see what we could learn about the deep structure of the crust in the area of the Bushveld complex. And so that's, for example, profile from A to B over here, showing how clearly you can see how the depth to the crust mantle boundary, the moho, gets deeper as you go through the center of the Bushveld complex. Over here, that's the profile from C to D, from the northwest to the southeast, and again, you see much the same picture. And also, I won't go into all the details of the crustal structure, but you can see what's coloured in over there in grey is where you have higher velocity rocks, more mafic rocks, towards the base of the crust. But of course, for the Bushveld, what we're interested in really is the structure in the top 10, 15 kilometres of the crust. And so that's the profile from E to F. But really, just briefly, the conclusion was over here that here are these two, I suppose you could say, competing models. And while over here, using these global earthquakes, the wavelengths are very long. They're many kilometers in length. So you can't expect to pick up things that are quite relatively thin. I mean, like just a kilometer or two thick. But you can work out what is the average seismic velocity in that part of the crust. And what it's clearly showed over here, that the interpretation we got from those long wavelength distant earthquakes, it was very much more compatible with the proposal that the Bushveld is in fact continuous and your moho is depressed than with the earlier model over here, which had a flat moho and had the absence of mafic layers in the upper crust. So that was a good result. Sue was very happy over here because it supported her result. Okay, let's move a little bit further. Let's move to Namibia. And one of the questions over here, and that's been around for quite a long time, has been what is the boundary over here of the Congo Petra? Who's interested in that? Well, the diamond mining companies, of course. So they gave us some money, De Beers and BHP Billiton and Rio Tinto, to put out temporary arrays of stations that you had in Angola, the DRC, Botswana, Namibia, and Western Zambia, to see if we could learn more about the limits of the Congo Petra. Because, of course, that area, it's covered by Kalahari sands, it's covered by jungle, and so nobody really knows how far the old Archean rocks extend. So that was the objective of this study. The person who did it, one of them was the Azangi Mangongolo, originally from the DRC. He's now working at the Council for Geoscience, busy on his PhD at present as well, working with us. But this is more his MSc study. So this is now using a different technique where we really use surface wave tomography. So over here on the left-hand side, you've got just a sketch over here showing you the main elements of the continent, the Congo Craton, the Karl Craton, the Tanzanian Craton. And what Zangi made use of over here on the right-hand side is you can see all the earthquakes. The earthquakes are in red over here, both along the mid-Atlantic and the mid-Indian ridges, and then also your earthquakes along in East Africa. And then all the other symbols that you can see over there, you can see are all the various seismic arrays we made use of. So he made use of the South African seismic experiment, the green triangles there. He made use of the Cameroon array. He made use of other networks that have been in East Africa and in Ethiopia. And what you do is if you draw a line between each earthquake and the stations at which it was recorded, and in the end, you find that you get an incredibly dense network of all these crossing ray paths. And so you use a method which is known as tomography. You try to explain the time it's taken for the wave to get from, say, the green earthquake to one of the seismic stations by breaking up its path into the speed it travels through different blocks and the time it's spent in every block. So what you do is you collect all this information, thousands, in fact tens of thousands of ray paths like that. You build a model made out of squares, out of cubes, so it's both in the crust and as you go into the mantle, and you try to explain that data. So you use a mathematical process known as tomography, and in the end you come up with a picture of again looking deep into the earth to see how the seismic velocity varies. Of course you've got to test this and see how well it works. Can you trust the model that you get out of it? So bottom left is the model. And what you do this by doing what we call a checkerboard test. So you put in a known model where in each square you allow the velocity to vary by perhaps 3% more or 3% less of the value, and then you trace your rays from each earthquake position, each actual earthquake position, you trace a path from there to each receiver where a wave was recorded. So you work out what theoretical travel times would be, you chuck in a bit of noise to make it more realistic, and then you see how well you can recover your model. And so at the top right and bottom right, you see examples of these checkerboard tests. And you see areas where you haven't got good coverage. Of course, you don't get good resolution. It doesn't work out. And also, if you make your squares too small, you haven't got enough rays going through them. It doesn't work out. So this is, again, not a high-resolution technique. You can pick up cells that are perhaps 80 or 100 kilometers on a side. Anything that's only 20 or 30 kilometers, again, working with long wavelengths, is not visible. Right, and this is over here, you can see the outputs of an experiment like this. So what we've seen over here, you've constructed from by inverting all these travel times through the Earth, you get a three-dimensional model of the Earth's crust, and upper mantle going down from, I suppose, near the surface down to perhaps 150 kilometers below. And so you see these are just slices that have been taken out of here, starting at 51 kilometers, then 61, 71, 81, 91, and so on. And so what you can see over here, if you look at this example over here, top one, you can see, here you've got, and it's color-coded in terms of whether your velocities are fast or slow relative to a standard average Earth model. If they are blue, that indicates they are faster than your average model, and that indicates that it's probably colder crust if you're just looking at the effects of temperature, but of course can be an effect of your composition. As you get deeper down, you go deeper, so this is looking at just below the upper mantle, and what we do is go deeper and deeper into the mantle, and what we're trying to see over here, of course, are the roots of our continents, and particularly in this case, it was looking for the roots of the Congo Petra. And so the purpose of this exercise was really to focus and see where the edge of that craton is, because really when one's prospecting for diamondiferous kimberlites, the model is that your best chance are the kimberlites that are on the Archean craton, but close to the boundaries, not in the center. So again, this was the purpose for mapping the perimeter of the craton in that area. Right, let's move on to something different over here. This is work that we were doing in Sudan, and this is Anada Al-Tahir. She's just finished her PhD. It's all examined and accepted, so she'll graduate at the next ceremony. So she's been shuttling between Wits and Khartoum and the USA as she's been working on this. And what has happened over the last few years is area around Sudan has not been an area in which it's been easy to work, but we've managed to put in a couple of stations in that area to look at all these young rift valleys. And now this is a very hot topic in Africa, because many of these young rifts in Uganda and in Tanzania and this area as well have proved to be contain petroleum deposits, oil and gas deposits. So there's a lot of interest in understanding the geometry of these rifts and how they form. So she had a few stations, about 4 stations around Khartoum, and so this was some just initial work to try to get a good idea of this, of the structure, the crustal structure and upper mantle structure in this area, and also how it connects. You've got this big structure called the Central African Shear Zone that runs across the continent all the way to the Central African Republic down and across to Cameroon, and see how this all works together. So this is all part of us, I suppose, expanding our network, our area of research further to the north. Again, she used receiver functions, and of course, when you use receiver functions, you see the red spot marks where her array was, and the earthquakes that she recorded were at distances between about 3,000 and 10,000 kilometers away. And again, you can see they come from different parts of the world. Some from Indonesia, some over here from the Atlantic Ridge, others in Asia. And so again, you can interpret the data looking at the energy coming in and piercing the MOHO at different points. Here she used a different technique, which we call HK stacking. And again, what you try to model, over here you can see your receiver functions from different azimuths and different distances on the right-hand side. And you're not just modeling the first S wave that comes after your P, but the reverberations in the crust itself. So that's the PS, and you'll see things like P, little ps. Those are the little reflections, the reverberations and echoes you're getting in there. So what you're trying to do is model that whole waveform for about 20 or 30 seconds after your first arrival comes in here. And of course, as in geophysics, you often find different models that can more or less satisfy the same data. So you've got to find out which one does it best. And so we form what we call an objective function, and we look at, and we do a whole lot of tests using different crustal thicknesses and different ratios of P velocity and S velocity, the average velocities in the crust, and so we see which gives you the best goodness of fit. So where you've got the bullseye over there, that is the best solution, that fits your data best, your whole data set over here, but it also gives you an idea of the ambiguity over here. So of course there's a trade-off between crustal thickness and VP-S-VS ratio. You can get different solutions would satisfy the data almost as well. So it's an objective way of trying to sort that out. So here again, it's an example of some of the data. You can see at the top there, you've got, say on the left-hand side, the black data would be your observed receiver function, and the red data is the fit of your model to it. And it's been done for two frequency ranges. The one on the top is a bit of a lower frequency one, and underneath we've used a different filter and got a higher frequency function. So we're using both, fitting, and we're not just fitting the time gap between them, but we're fitting the detail of the waveform, the amplitudes of the waveform, and not just the first conversion, but all the other conversions that come after it. So these are the kind of advances that have come in the last while. And then in the second row over there, you see what we call our group velocities. Those are surface waves and the way in which they've been dispersed. So we're doing a joint inversion of them. And what we're doing over here, of course, and so you see there are four different sets over there, and they represent different azimuths and different distances. So again, that's allowing us to look at not just as you could say, one average crustal structure underneath that station, but looking at it in 3 dimensions. And then at the bottom you start off, you'll see there's a grey curve over there, which is just a starting model that we started with. And then the red model over here is what would come with the best model that satisfies our data. So again, NADA was able to come up with the first data, in fact the first research that had been done in this area of Sudan, and the first depth to Moho, and the first idea of deep crustal structure and upper mantle structure. Okay, the last topic that I'm going to touch on today is looking at some of the work we've done here on the East African Rift System. This is Gabriel Mulibo. He was a PhD student who spent most of his time at Penn State University. He's now at the Nelson Mandela University of Science and Technology in Tanzania as a lecturer there. And we'll look at some of the work that he has done around the East African Rift System. Now, I suppose the big question that we're trying to answer, it's been well established, we've known for the last 20 or 30 years, that underneath Africa, in the lower mantle, there's a big shear wave anomaly. And it's become known as the African superplume. The shear wave velocity is a little bit lower than what it is elsewhere in the lower mantle. There's a corresponding anomaly underneath the Pacific over here. Now the question is that due to differences in temperature, or is it due to differences in composition, or both? Is it something that's just a short-lived feature, or is it a long-lived feature? Is it in any way connected with the East African Rift? So these are some very first-order questions that we are trying to answer over here. So over here, these are various models that have been produced over the last 10 or 15 years. But in order to answer some of these questions, what we really need to do is have better resolution data. And the only way to do that is to have more stations and record more earthquakes. So that's really what we've been doing with AfricaArray over the last 10 years, is putting in more and more stations, and part of the knowledge will be contributing towards these structures. So this is just an example over here of some of the temporary deployments that we've been involved with in Ethiopia and in Kenya and Tanzania. And over here now some of the more detailed tomographic inversions for these different regions. And what you can clearly see over here is, and again the color codes we use are, if it's a hot color, a red color or a yellow color, it means your seismic velocities are slower than normal, and that means everything else being equal, that indicates the rocks are a bit hotter, because then the S wave travels more slowly. And what you can clearly see under here, under the areas where there is the rift, that you see areas of lower shear wave velocity, which indicates that your rocks there are hotter. Okay, well that seems to make sense. Of course, one of the questions is the hot rocks that are driving the rifting, do they originate just by convection in the upper mantle, or do they also penetrate it? Is it a feature that extends down into the lower mantle? And so that was past work, Now, in Gabriel's studies, he used other arrays. You can see the various AfricaArray networks that were put out in 2007 and 8. We were up there in Uganda. In 2008 to 10, you can see we moved here to southern Tanzania. And in 10 to 11, we had some over here towards the coast. And then we've also had others over here in Zambia, okay, which were part of that De Beers network. So a lot more data sets have been put in the last 10 years. And again, one looks at, that's our receivers. Where do you get your energy from? Okay, well, we were doing both P-wave tomography and S-wave tomography. And there are slightly different criteria for the stations you choose. But again, Africa's well situated. You have Africa itself isn't very seismically active, but there are a lot of sources of earthquake energy that illuminate Africa, particularly the mid-ocean ridges, the area around where Africa's colliding into Asia, and of course in Chile, and around Indonesia. So there are lots of sources that could be used in order to look at the tomography. And of course, when you use tomography, you don't only use the waves that travel, you could say, through the mantle like this, but you also use waves that can bounce off the core and then come up more steeply and illuminate the crust from below. So there are different wave sets that one uses. And so this was the earthquakes that were used. That's why if you're a seismologist, like right now with our stations out there, every morning I will look on my smartphone and get to one of the sites and see what earthquakes happened in the last 24 hours. Were they any bigger than magnitude 5.5? If so, that's good news. This will be contributing to our data set. Right. So, every day something comes in. Right, and again, what one does over here is you construct all those ray paths cross underneath this area where you've got a lot of stations over here. One works out a model, a velocity model, which you compare to a standard Earth model over there, where you're looking at changes. In this case, we're showing changes in your shear wave velocity anomaly. So it's up to 2% or 2% more fast or slow. So it's not a huge amount, it's quite subtle, but you can pull it out in a very robust way. On the top, you see first a picture, a slice through here, a depth slice of 200 kilometers, then at 400 kilometers, then at 600 kilometers. And what's outlined here, that potato in the middle there, that's the Tanzanian craton, and you can see how it's surrounded, particularly at 200 kilometers, you can see it's surrounded by the oranges and the reds, and that indicates those are the areas where your, I suppose you can see down here in the slices, you've got your hot rocks coming up to the western branch of the East African Rift and the eastern branch, and you can see how deep over here your Tanzanian craton extends. You can see on the right hand one here, when you get down to a depth of 600 kilometers, you're already right through the craton and you see the top of the plume or the hotspot. So that is one of the big questions over here, was, is this western branch and the eastern branch is being fed by a plume which has got a relatively thin conduit, or is the super plume which has got a big fat thing feeding it? Now, one way in which to distinguish between these is looking at the nature of our 410 and 660 kilometer discontinuities. And these are boundaries in the mantle where you have a change in your seismic velocity, which you relate probably to phase changes in the minerals that you get there. Now, if the whole area is heated up, like in the super plume, it will mean the position of those discontinuities will change. The thickness of the transition zone will become smaller like that. So the question was, could we see that in the data? Here's the mineralogy on the left-hand side, but really what we're looking at over here is if you're in an area with a low temperature, you'll find that the thickness of that discontinuity, or the distance between the boundaries, should increase. On the contrast, if it's an area where you've got high temperatures, they should come closer together. How are we going to map those discontinuities? Well, we're also going to use this receiver function method, only now we're not looking for conversions at our MOHO, but conversions of our P waves to S waves at the 660 and 410 kilometer discontinuity. So again, it's the same idea, just looking further down your seismogram. Not just 5 seconds after your first arrival, but tens of seconds afterwards. Where are these points, these conversion points sampled? This is what we call the Pierce point for our P to S conversions. And on the left-hand side, we see the Pierce points for the 410 kilometer discontinuity. And on the right-hand side, you see the Pierce points for the 660 kilometer discontinuity. So you can see in this area, around Tanzania over here, we've in fact got pretty good coverage of, and that's because we've got lots of stations and we've got lots of earthquakes, and where those conversions would be taking place. And so we are able then, at each one of those dots, those green dots on the left-hand case, or the blue dots on the right-hand side, get a depth to that discontinuity. So, what does that tell us? You'll see over here on each one of them, we've got some profiles, A prime, and B prime, and C prime. What does it look like? And this is really the position of the receiver functions that have been plotted over here. So for the profile from A to A prime over here, you can see over here, those where it's coloured in dark over here is the position of that conversion point converted to depth. And what you can see over here is really, and then down at the bottom, what we've plotted over here is the transition zone thickness. So working out the difference between the top conversion and the bottom conversion. And you can see over here that it's, in fact, your transition zone gets thinner as you go through the centre over here. Okay, you get a lot of red colours over here, which indicate a transition zone thickness of only about 190 to 200 kilometres. So over here, this is the cartoon on the right-hand side showing you the same sort of picture over here, that you've got quite a thick zone, so, a couple of 100 kilometres across over here, where your transition zone is thin. And certainly what this data would support then is that you don't just have a pretty little plume coming through here with a small conduit that spreads out like a mushroom above, but you've got a big thermal upwelling. Right, so that's the, I suppose you could say, the preferred model over here. But the question is really, how well can we resolve that? We can see that depression over here in these 410 and 660 kilometre discontinuities. But in our tomography model, it also seemed to show as if this low velocity zone was cutting right through here. But we know our resolution isn't so wonderful with these methods. You're dealing with wavelengths that are tens of kilometres long. So what we had to ask ourselves is, could we be sure that we had that the two are connected, or could there be a gap through it, but just our technique doesn't let us resolve? So again, one puts in a theoretical model. So over here you can see there, Gabriel put in 3 models over here. On the left-hand side, he put in 2 low-velocity blobs that they were separated by 100 kilometres. Then he had another model in the middle over here where they're separated by 200 kilometres, and then on the right-hand side by 300 kilometres. And then using the real position of all the earthquakes and the real positions of all the seismic stations, he traced ray paths through there and worked out what the arrival times would be. Added a bit of noise to those synthetic measurements, and then tried to see how well he could recover his model. Okay. So on the left-hand side, you see just the way it works. You don't get perfect resolution. You can't tell. It looks as if they're connected over there, but in fact they can't. So it means there could be, in fact, 100 kilometre separation between those 2 blobs, with a sort of a normal velocity in between, and you wouldn't be any the wiser. Okay, we put this. When you get to 300 kilometre separation, you can be pretty sure that you can see they're not well connected. So again, always in geophysics, you're stuck with uncertainty in your data, some ambiguities, and you always, if you're doing honest science, you need to explore that and not just make a simplistic interpretation that fits your preconceived idea over here. So we can see it looks as if the 2, they certainly, if there are low velocity zones in the Earth, which there certainly are, they could be perhaps as close as 200 kilometres and maybe have a gap of maybe between 100 and 200 kilometres. We wouldn't be any the wiser. So we can't be sure of that. How do we resolve that? Well, we can get more data, but up to a point you're limited by the wavelengths that you're recording, and the Earth acts as a filter, and you can't just sucks out the shorter wavelengths. It's the way it works, and so there are limits to the resolution you can get. So we pretty much feel we've pushed this method as far as we can get. So really, in conclusion over here, we're just looking at the East African rift over here. Some major new results over here, but we say from looking at the body wave tomography, we think there's evidence for a through-growing mantle low velocity anomaly, although we cannot rule out that there's a 200 to 300 kilometre separation of the upper and lower mantles. We cannot rule that out. Okay, but that's from the tomography data, and then we will use the separate approach using receiver functions. Okay, and there, by looking at those I suppose the positions of those transition zones, it would seem to indicate that the upper mantle low wave velocity anomaly beneath Eastern Africa is connected to the lower mantle. And looking at both of them together, it could be interpreted, we could explain that thinning of that transition zone, the distance between those, the 410 and the 660 kilometers, could be due to an increase in temperature of the order of maybe 300 degrees, 300 Ks. And so over here, the conclusion is over here that so far our data, and we've got, I suppose, good data over here, that seems to link that our rifting that you see on the surface seems to be connected, in fact, to this deep structure under southern Africa, the African superplume. So that's big finding, something we can state with far more confidence than ever before. So just in conclusion, what are we doing in AfricaArray? These are just some of the projects that are currently underway. As I said, we've finished this deployment of stations in Comores, Madagascar and Mozambique. And so we're busy working on this data. Runt over there in the back, he's from Madagascar, he's a postdoc with us. We've got 2 of our PhDs from Madagascar. They've just spent a couple of months here, and they're in Penn State right now. That's Tsitsi and Finitra over here, and Ilios from Mozambique. He's been working on some of the Mozambican and Tanzanian data. And in particular looking at these, instead of having a P to S conversion, which we've spoken about so far with our receiver functions, you can do the same with your S body wave, which gets converted to your P wave. Why would you want to do that? Well, where you've got a lot of layering in the crust, like sedimentary basins, you get a lot of reverberations, and they muck up your P to S conversions, and it comes out a bit better with your SP conversions. As I said, we've got 25 stations in Botswana. We're doing that with the European Union funding, together with the University of Twente. We've just put 10 stations in Namibia, funded by De Beers, and that, looking at again, getting more detail over there. What we're also doing, and we've just had some American students here for our field school earlier last month, but we are putting in some stations more stations in the bushveld. We're densifying those stations. Previously they were 100 kilometers apart, and now we're putting some in between to get some more information here. And also we put in some of those stations alongside bushveld reflection seismic data to see how much we can enhance the resolution. And this ties in together with the planned ICDP project, the International Scientific Drilling Program. Sue's over in Germany right now writing up the full proposal for that. We also have some work that we're doing around nuclear waste disposal. And as you know, South Africa's maybe going to build new reactors. We only have a low and intermediate level waste disposal site at Falpit in the Macroland, and so we're doing some monitoring that would allow perhaps us to license it for high level waste. So we have a few seismic stations out there. We're also using our AfricaArray data that we've collected over the last decade along the East African Rift, and using that to improve our assessment of seismic hazard and earthquake risk. So we have a project here that's funded by the USAID, and the main researcher on that is George Mavonga, who's an ex-PhD student of ours based at the Dover Volcanic Observatory in the DRC, and we're working together with the Global Earthquake Model program in that case. And we also try to kickstart our work in atmospheric science, climate change, and space weather. So right now this is just where some of our current stations are over here, and you can see the green symbols over there indicate our 25 stations in Botswana, and the orange symbols are 10 stations in Namibia. We put them in February over here, and this is just some of us. The one site that's near Omaruru out there at a high school, and we're busy digging a hole and putting them in place. And that's the team over there that put them in, and Runt will be going back up there in a week or two's time, because 3 of the stations aren't functioning properly, so he's got to go and restore them to health. So that will hopefully gives you an idea of the scope of the work that we're doing in AfricaArray, what our objectives are, and the kind of science that we're doing. But certainly I think we started in 2005. Next year will be our 11th annual meeting, and we've seen a big advance in the amount of data we collected, the number of stations we've been doing, and the products that have been coming out of this. Thank you.